Okay, Unit 4, Day 6. Today we will solve logarithms. So moving right along with the idea of logs. Okay, so we're going to do a quick warm-up, just review properties of logs, and then see how the change of base is going to help us to evaluate problem number 2. Okay, so for this first one, we're going to expand. So you're going to need to remember your properties. The first thing I see, though, is we can make this a little bit simpler by simplifying our z to the 12th over z to the 4th and make that z to the 8th. So remember, the reason I can do that is because all of those expressions on the bottom are being multiplied. If they were being added or subtracted, then we would not be able to simplify that. Okay, so now I'm going to apply my quotient property. So I have log base 3 of z to the 8th minus, and remember from yesterday, I need to put this in brackets since I have multiplication on the bottom. And to make things a little quicker, we can do the 6th root of y is y to the 1/6. So I have minus log base 3 of x to the 3rd plus, since it's multiplication on the bottom, it's the product property, log base 3 of y to the 1/6. So now I can distribute my negative sign and bring those exponents down front using my distributive property and my power property. So the 8th is going to come out front. I have log base 3 of z minus 3 log base 3 of x minus 1/6 log base 3 of y. So sometimes it's a good idea to go ahead and put these arguments in parentheses so we know that they go with the logarithm. All right, so there's that one. So on this one, I know that you could put this in your calculator and evaluate it, but to apply the change of base formula, they're going to ask us to change this to base 2. So I can apply that change of base, and I can change this log base 2 of 32 over log base 2 of 4. So once you do that, hopefully you recognize that 32 is a power of 2. So 2 to the 5th is equal to 32. And on the bottom, I've got 2 squared, which is equal to 4. So log base 2 of 32 is equal to 5. And log base 2 of 4 is equal to 2. And I've evaluated that logarithm using my knowledge of logs and not my calculator. All right, I've gone ahead and filled all this in just because it would be quite time consuming to do this via video. Okay, so we're going to solve some logs. So we have 3 methods. So the first method makes it nice and easy. If you have an equal sign between your logarithms and your logs are the same base, you can pretty much ignore your logarithms and just solve within parentheses. It works the same way if you had 2 to the power of x equals 2 to the power of 5. I can ignore my bases and just say x equals 5. So exponent properties and log properties go hand in hand. The second one is to apply your log properties and then produce an equation like method number 1. Or we can actually use algebraic techniques, isolate the logarithms, change to exponential, and solve. Okay, so we've got to remember that our logs are, our domains are restricted. So if we have a logarithm, we're going to determine the domain first, and then we're just going to look for extraneous solutions once we get to our final answer. Okay, so we're going to solve this one. So this one's method number 1. I've got logs on both sides, and my base is 4. So I can ignore my logarithms and just do 3x minus 5 equals 15. The one thing I need to do is think about the domain. So 3x minus 5 has to be greater than 0. So x has to be greater than 5/3 when I get my final answer, or it's extraneous. So I'm going to add 5, divide by 3, and x equals 20 over 3, which is greater than 5/3. So that answer should be just fine for that one. Okay, so this second example, I need to apply my log property here. So remember, that would be my quotient property, where I can combine that to a single logarithm. So I get log base 4 of 12 over 5x equals, and I'm going to go ahead and change my multiplier here back to an exponent. Log base 4 of 5 to the 3rd. So here I know my domain of this logarithm has to be greater than 0, so x has to be greater than 0, which kind of makes sense for my denominator down there. I know x can't be 0. So always look at your logarithm first and determine your domain. Okay, so now that I have the same log base 4, I can ignore my logs and solve my argument. So I've got 12 over 5x equals 5 to the 3rd, which is 125. If I multiply both sides by 5x to eliminate that denominator, I get 12 equals 625x. Divide by 625, and I get 12 over 625 equals x, which is greater than 0. So that would be the solution to my problem. Remember, you can always go back and plug it in if you were ever wondering. All right, so on this one, there is a typo. So I forgot to put the 3 in front of there. So on this one, I'm going to determine my domain first. So this piece of the logarithm, 7x plus 1, has to be greater than 0. So x has to be greater than negative 1/7 when I get my final answer. Remember, the domain of your parent function for a logarithm is greater than 0 because there's that vertical asymptote that sits there at x equals 0. Okay, so I need to isolate my logarithm. So I need to isolate this entire piece before I can start solving. So I'm going to have 3 log base 2 of 7x plus 1 equals 13 plus 5, which is 18. I'm going to divide by 3. So log base 2 of 7x plus 1 equals 6. Once I get that logarithm isolated, I have to change to exponential. So my base is 2, my exponent is 6, and the other side of the equal sign is my argument, which is 7x plus 1. So 2 to the 6th power is equal to 64, equals 7x plus 1. If I subtract and divide by 7, I get 63 over 7 equals x, or x is equal to 9. Go back and check that with my domain restriction. 9 is definitely greater than negative 1/7, so I have an answer for this problem. Okay, so same idea here. I need to determine my domain first. So 5 plus 2x has to be greater than 0. 2x is greater than negative 5. X has to be greater than negative 5 over 2. Otherwise, that logarithm is undefined. So I'm going to divide by negative 4. I need to isolate this piece of the log. So I have log base 3 of 5 plus 2x. Negative 16 divided by negative 4 is 4. Once I have that logarithm isolated, I change to exponential. So base 3 to the power of 4 equals my argument, 5 plus 2x. 3 to the 4th is equal to 81. Subtract 5, I get 76. And here I get x is equal to, oops, messed that up. That should be a plus. Miscopied that, sorry. 76 divided by 2 is 38. Okay, there's some solving of logarithms. So now the next piece of today's lesson is applications of logarithms. So we have two major applications of logarithms, and one is determining earthquake magnitude, and the other one is determining the decibel level of sound. So for earthquake magnitude, we have a formula, and its magnitude is equal to the log of I over I sub 0, and I'll define these variables for you. So m is the magnitude. That's based on your Richter scale that you've heard a little bit about, I'm sure. This I is the intensity of the earthquake. I'm just going to write quake here. And I sub 0 is the intensity of the threshold. It's called the threshold quake. Basically, what the threshold is the smallest detectable earthquake. Okay, so the smallest detectable earthquake, and you'll see how that works as we do some of these examples. I think I spelled detectable wrong. It should be ABLE. Okay, so for sound decibel, the formula looks like this. This stands for decibels, and it's equal to 10 log 10 of I over I sub 0. Okay, so those I variables mean exactly the same thing as what they do for the earthquake. And then the capital D, or the D capital B, is just the abbreviation for the decibel level of the sound. Okay, so you're going to need these formulas when you're taking your PFAs. So make sure you make a list of your formulas or have your notes out. And feel free to use them. Okay, so before we do some problems, this is just kind of an interesting little slide that was thrown in here. And it's just about the magnitude of the earthquake. So anywhere from 0 or 1 to basically greater than 9 or anything higher than 9. So it gives you a description of them, whether it's a micro earthquake or a minor or a light or a strong. It kind of gives you an idea of what kind of damage that earthquake can cause based on the magnitude of it. And then over on the side is just your average frequency. So it's just kind of an interesting slide to look at. It may help you on the project over this unit as well. So take a minute and just look through that. Okay, so we're going to solve a few basic problems, and then tomorrow we'll do a few more problems. Okay, so a conversation is 89,000 times more intense than the sound threshold. So remember, your sound threshold is I sub 0. The conversation this problem is talking about is the I, or the current decibel level that we want to find out. It wants to know how many decibels is the actual conversation. So if I think about my intensity, 89,000 times more, so that would be 89,000 times my threshold is equal to the conversation. So that little formula is going to help us a little when we work on our decibels. So I'm just going to use the original formula that I gave you on the previous page. It's just 10, sorry. So remember, that's 10 log intensity over the intensity of the threshold. So if I take this and substitute it for I get my decibel is equal to 10 log 89,000 I sub 0 over I sub 0. So my I sub zeros can cancel. So basically, I'm just taking 10 log of 89,000, which comes out to about 49.5. So the decibel level of that conversation is about 49.5. Just a little side note, a normal conversation is about 60 decibels. Okay, so now we're talking about an earthquake, same idea. An earthquake is about 179,000 times more intense than the earthquake threshold. What is the rating on the Richter scale? So same idea as my decibels. I know that my current earthquake is equal to 179,000 times the threshold, which is I sub 0. So for my magnitude, that's equal to just log, there is no 10 in front of it, over I sub 0. So if I substitute I as being 179,000 times I sub 0, again, my I sub zeros are going to cancel. So I'm just taking the log of 179,000, and that comes out to about 5.923 on the Richter scale. And if you look back at that little chart, that is just considered a moderate quake. And that's the end of, oh, I thought we had some more. Okay, so that's the end of today's. Tomorrow we'll get a little bit more involved with using these two formulas. So after we do that, you should be ready to take the PFA over logarithms. So everybody have a great day.